In this lecture, we talk about functions. What do we mean by function? We learned from last video that we can express some relation between two elements as ordered pairs. And we write the ordered pair as in this form: x, y, x comma y. This variable is called the independent variable, and this variable here, y, is the dependent variable. So we imagine that we have two sets, x and y, and there are some elements of x here and some elements of y here, and we have some relation between these elements. So this is called in general relation between x and y, and this relation can be represented as ordered pairs. For example, if this point here is A, this point B, this is C, this is D, this is 1, this is 2, this is 3, etc. So we may write it this way: A is related to 1, B is related to 3, D is related to 2, and so on. And we may put it in a set notation. So this is called relation. Now we have a special case of relations. Relation in general is set of ordered pairs. So it's a set of ordered pairs. This is the relation. This is what we mean by relation. So these are ordered pairs. Order is important. And now, in order to define the function functions are special cases of relations. So what do we mean by function? A function is a relation or is a rule that assigns to each element of a set X exactly one element or value. Let's use the word value here, of Y. So when we talk about functions, we usually deal with numbers. So we have a relation between two sets, and each element, we assign to each element of X exactly one element of Y. So that means this element A is related to 1, but A cannot be related to 2 as well. So it's just assigned to one element. It has one output for each input. These are inputs. X represents the inputs and Y represents the outputs. For each input, we only have one output. So this is not a function, this is a relation. So keeping this in mind, we can decide whether a given relation is a function or not. Let's take some examples. Before that, let me just tell you something about a notation or about a terminology that's usually used. Actually, we call these X values as inputs and the Y values are outputs, but we usually call them, when we talk about functions, we call this domain. X is the domain and Y is the range. So that's the terminology that we're going to use when we talk about functions in general. Okay, so for functions we have domain and range. Domain represents the inputs, range represents the outputs. Now let's take this comprehensive example. We want to determine which of the following relations is a function. Part A, we have this set X and this set Y, and we have some relation between 1, 2, 3, 4, 5, 6, and 1 is related to 4. 1 is related to 5 as well. 2 is related to 6, and 3 is related to 6. B, we have this X, this set Y, we have 2, 4, 6, and here 3, 1, 2. 1 is related to 3, or 2 to 3, 4 to 2, and 6 to 1. And we have this table, X, Y, some values of X, -3, -2, -6, and some values of Y. Actually, it's the same value, 5, 5, 5. D, we are given this relation, 10 related to 6, 16 with -1, 36 with 6, 10 with 1. Is this a function? And we'll continue. But for now, let's answer these questions. Is the part A represent a function or just a relation? Actually, if we look at this input, 1, this gives 2 outputs, and that's not allowed. We should have exactly 1 output, exactly 1 value of Y related to a given value of X. So this is not a function. What about B? 2 is related to 3, 4 to 2, 6 to 1. Each input gives 1 output, so yes, this is a function. What about C? -3 is related to 5, -2 is related to 5, -6 is related to 5. Now look at this. We have for different outputs, we have same input. Different inputs, we have same output. And that means we don't have any problem, because the definition says for each input, we only have 1 output. For example, -3 is related to 5. This is 1 output for -3. But if we have -3 and 6, this is not a function, because for same input, we got 2 outputs, and that's not a function. But here for this problem, we don't have any restrictions on the Y, the values for Y, or the corresponding values of X. So -3 is related to 5, -2 is related to 5, -6 is related to 5. So that means we don't have any problem. Each element, for each input, we only have 1 output. So we have 1 arrow comes from the input to in the direction of the output. So this is a function. What about D? If we look at the D, we should not have some repetition on X, because if we have repetition, that means 1 element is related to 2 outputs. And as we can see here, we have 10 related to 6 and 10 related to 1. That means we don't have a function. No, this is not a function, because 1 output gives 2 outputs. 1 input gives 2 outputs, and that's not allowed. Now let's add some examples. What about this? This is X, this is Y. We have E, X, Y, and Z, and we have M and N. E is related to M, X related to N, but the other ones are not related to anything. So that means we don't have a function here. No, because the function is a relation. This should be a relation that assigns, or a rule that assigns to each element, each input, to exactly 1 output. But as you can see, those 2 inputs don't have any outputs. So that means we don't have a function. Another example. Now, if I give you a graph of a function, a graph of some relation, if the graph looks like this is y equals f of x. This is x-axis, this is the y-axis. Now, is this a function? Now, if we give you a graph, then you can use the vertical line test to determine whether this is a function or not. Now, if you look at this, the elements on x are called the inputs. Those are inputs. And the elements on y are the outputs. So you can see here, if you choose any two values, any different values of x, you get one value, corresponding value of y. So we don't have one value of x that's related to two values. So this is a function. Or you can simply use the vertical line test. So the vertical line test says any vertical line, if you graph any vertical line, that vertical line must intersect the graph in at most one point. As you can see, it intersects here at one point. If you graph it here, it intersects at one point. So by the vertical line test, which says every vertical line must intersect the graph in at most one point. And as you can see, this graph passes the vertical line test, so yes, it's a function. What about this? I give you this graph. Is this a function? Now we try the vertical line test. If we graph a vertical line here, it will intersect the graph in more than one point, here and here. So it does not pass the vertical line test. That means not a function. It's a relation, but it's not a function. Or if you look at the value, this value here, this point here, this gives two images, two outputs, this output and this output. So two outputs are associated to one input, and that means this is not a function. Now, sometimes we give you a rule. For example, y equals square root 5x plus 1. Is this a function? We can either graph this relation and use the vertical line test, or we can try some values. Now, if we want to try some values, we can see it's easily can be seen that if we choose different values of x, for example, -1 and, or let's choose one value, -1. -1 gives y equals square root 5 times -1 plus 1, and that's square root -5 plus 1. This is impossible because we have negative value inside the square root. So these values are not defined. So we should worry about what's called domain of the function. Not all the values are allowed here. Some values are allowed, other values are not allowed. So, but as long as we have for each input, we only have one output, we are in the safe side, and that means it's a function. For example, if we choose x equals 1, this should give me one value for y. Y equals square root 5 times 1 plus 1, and that's square root 6. This is one value of y. So for each input, we only have one output. Now, if we want to prove it using the vertical line test, we need to graph this function. Now, how to graph this function? We find the zero of this function, 5x plus 1 equals 0, and then we solve for x. 5x equals negative 1, and then divide by the coefficient of x. X equals negative 1/5, this point here. And then the graph looks like this. This is the graph of the relation, let's say relation y equals square root 5x plus 1. Now, if we try the vertical line test, any vertical line will intersect the graph in at most one point. So it passes the vertical line test, VLT. So yes, it's a function. Now, look at, this is a good example, the part H. As you've seen from this example, when we substituted x equals negative 1, I got y equals square root 5 times negative 1 plus 1. I substitute here. And that gives us square root negative 5 plus 1, which is square root negative 4. And that's not allowed because we can't have negative value inside the square root. So that means this value should be excluded from the domain, from the inputs. So the inputs are not all the real numbers. We have some restriction. Now, how to find all possible values or accepted values, all allowed values for x? In order to do that, if we have square root, we can find it this way. We can look at the expression inside the square root, and we want to find the domain of y. We set the expression inside the square root greater than or equal to 0. 5x plus 1, we want this to be greater than or equal to 0. Because if we have square root 0, that's 0. Square root of any number greater than 0, that's allowed. That's okay. But square root of any negative number is not allowed. That's why I used greater than or equal to 0. We want the expression inside the square root to be greater than or equal to 0. Now we solve this inequality as we learned in the previous chapter. 5x is greater than negative 1, and then x greater than or equal to negative 1/5 by dividing by the coefficient of x. So we have negative 1/5, and it's closed at this point because we have equality here. Greater than, that means to the right. So what is the domain? All these values are allowed, so the domain is negative 1/5 to infinity. All these are possible values and accepted values for x, but any values less than negative 1/5 are not allowed. Now, what is the range of this function? The range, if we look at the function, the range the y values. The y values start from this height to infinity. As you can see, this graph goes to height infinity. So from here, this is the range. This is the range. So the range is, the height here is 0 to infinity. That's the height. It starts from 0 and goes to infinity. So from 0 to infinity, this is the range. The domain, we look at the x-axis, where's the allowed values. The allowed values are these values here, starting at negative 1/5. Okay. Now let's take some exercises. Now for this function, we want to find the domain. We already solved a similar problem. We just look at, since we have square root, we look at the expression inside the square root. We want this to be greater than or equal to 0, and we solve for x. We solve this inequality. So we divide by 8, we get x greater than or equal to negative 1/8. So this point here is negative 1/8. It's closed because we have equality. Greater than or equal to the right. That means the domain is negative 1/8 to infinity. and the range is 0 to infinity, because the smallest value of this function is -1/8. If you substitute -1/8 here, you get square root 8 times -1/8 plus 1, and that's square root of 8 times -1/8 is -1, plus 1 is 0, square root of 0 is 0. So the range is 0 to infinity. Now what about b? For b, we have a fraction or a rational function. If we have a rational function, we only worry about the domain or the denominator. Now, here in this problem, we're asked, how do you know if this is a function or just a relation? If for each value of x, there's exactly one value of y, that means it's a function. This is the answer. For each input, there is exactly one output. You can try any input, you get one output, except at x equals 9. So it's a good idea to determine the domain. To determine the domain for rational functions, we just look at the denominator and we set the denominator equal to 0, not greater than or equal. We use greater than or equal for square roots or even roots. But for rational functions, we look at the denominator, we set the denominator equal to 0, and then we solve for x. And the value that we obtain here is not included in the domain, should not be included in the domain, because this value makes the denominator equal 0, and that's not allowed. So everything except 9, so that's why we put it in, we put an open circle here to say that any value here except the 9 can work. So from -infinity here to 9, it's open at 9, because as you can see, we have an open circle, union 9 to infinity. So this is the domain. Now another problem. Now if we are given a function, if we know that we have a function, then it becomes a good idea. It's a good idea to write it as a rule. For example, f of x equals -3x plus 4. This is a rule for a function. And if we know the rule, then we can find the value of the function at some points. For example, here, f of 0. That means the value of x is 0. So we just plug 0 into this formula or rule, and we get 4. What about f of 1/3? 1/3, we just plug 1/3 into the function, and we get -1 plus 4, which is 3. Now let's plug m. F of m is -3m plus 4. Let's plug -4. F of -4 equals -3 times -4 plus 4. And that's 12 plus 4, which is 16. So these are the outputs. The inputs are 0, 1/3, m, -4, and these are the outputs. Now we want to write this equation as a function using the notation f of x. The notation f of x is the same as y, so we can replace y by f of x. So we write this as f of x plus 3x squared equals 5 minus 5x. I just replaced y with f of x. And then we need to bring this to the right-hand side. I mean, we need to isolate f of x in order to write the equation, the function. So f of x equals, when we bring 3x squared to the right-hand side, it becomes negative 3x squared, and we already have -5x, and we already have 5 on the right-hand side. And that's a rule of a function or formula for this function. Now we want to give an example of a constant function. Constant function, that means it does not have a variable x in the formula. So f of x equals 5 is a constant function. And when we graph it, this is x-axis, this is y-axis. When we graph f of x equals 5, it's a vertical line, is a horizontal line at y equals 5. As you can see, for any value of x, we have same value of y. So that's why the function is called constant function. Now an example of a linear function, f of x equals 2x plus 1. This is a linear function because the number above x, or that's called the degree of the function, the degree is 1. Quadratic function, we want the power of x to be 2. So, and we can add any terms here, but the highest power should be 2. This is a quadratic function. This is a linear function. This is a constant function. Now, the slope. What is the slope of the function, of the linear? Now we are focusing on the linear functions. And I mean by linear function, a function that can be written as f of x equals ax plus b. For example, f of x equals 2x plus 1. This is a linear function. The power of x is 1. Now we want to find the slope. What is the slope? The slope is given by this formula. M equals y2 minus y1 over x2 minus x1. So we need to name the points. This is x1, y1. This is x2, y2. And then we find the slope. M is y2. y2 is 12 minus y1. y1 is 3 over x2, 7 minus x1, negative 1. So 12 minus 3 is 9. 7 minus is plus. Plus 1 is 8. This is the slope of the line that passes through the points negative 1, 3, and 7, 12. Now we want to find the slope if we are given a formula. If we are given a formula, the slope is the coefficient of x after writing, this is very important, after writing the equation or the formula in the standard form. Or after putting the formula in the standard form, that means we need to isolate y. So we need to isolate y. Let's subtract 5x from both sides. We get negative 4y equals negative 5x plus 20. And then we divide by negative 4. So divide both sides by negative 4. That means we divide each term by negative 4. We get y equals 5/4 x 20 over negative 4, that's negative 5. Now this equation is written in the standard form. I mean by the standard form, y equals ax plus b. And actually this is written in this form. This is a and this is b. Now the coefficient of x is this. This is the coefficient of x. This is the slope. This is m. So m equals 5/4. So we need to write the equation first. If it's not already written in the standard form, we need to write it in the standard form, and then we determine the coefficient of x. That will be the slope. Now we want to graph a function. If we want to graph a linear function, how to graph it? In this case, we can make a table and we can choose some values. Let's choose x equals 0 and y equals 0. As you can see, y means f of x. So when x equals 0, f of x, which is y, equals 1/4 times 0 minus 2. This is 0, we get negative 2. So 0 with negative 2, this is 1 point. 0 and negative 2, this point here. And then we have y equals 0. Y equals 0. When y equals 0 here, we have 0, y is f of x. 0 equals 1/4 x minus 2. And then we solve for x. So let's add 2 to both sides. You get 2 equals 1/4 x. And then multiply both sides by 4. This gives 8 equals x. So x equals 8. So the ordered pair is x 8 and y 0. So 8 with 0, if this is x8 with y 0, that means this point here. And then we connect these with a straight line. This is how we graph this linear functions. Now what is the domain of the linear function. The linear function has domain negative infinity to infinity. As you can see, if we project this line onto the x-axis, this will cover the whole x-axis. That means, and that's the domain. The domain represents the values on x-axis, the allowed values on x-axis, or the values that have outputs or images. So that means the domain is negative infinity to infinity. Now, what about the range? The range is the values on y-axis after projecting the function. So as you can see, we can project these values onto the y-axis, and that should cover, as we extend this, should cover the whole y-axis. That means the range is negative infinity to infinity. Another example, we want to graph the line that passes through a point. We are not given a formula here. We are only given a point where the function passed through 2 and negative 2, this point here. And we are given a slope. Now, how to solve this problem? We can either formulate a function, a linear function, and then graph it as we did in the previous example, or we can just use this information. So we have a point 2, negative 2. We need another point in order to graph a linear function. So because in order to graph a linear function, we just determine 2 points and connect them with a straight line. So here we have 1 point, which is 2, negative 2, and negative 3, 2. Now, how to deal with this? This slope, negative 3 over 2, this is m. This is called rise, and this is run. So rise negative 3, that means we move down 3 steps, 1, 2, 3 steps. And then run 2 steps to the right, 1, 2, that means this point here. This point, which is 4 and negative 5, and then we connect them with a straight line. So this is the line, the graph of the line with this slope, and the passes through the point 2, negative 2. If we want to graph the function, we can graph the function y using the sum equation y minus y1, but we haven't dealt with that formula, so we just graph it this way. Now we have another example, or the last example talks about the average rate of change, and we have the points 0, 0, 3, and 3 here. We have this graph of a function, a linear function. So we want to find the average rate of change. The average rate of change is given by f. If we have 2 points like AB, A1, B1, A2, B2, or x1, x2, let's use x1 and y1. So this is x1, y1, or xy and f of x, fy. I mean x and x1 and f of x1. X and f of x. And actually, there are different formulas for this, but let's write it this way. F of b minus f of a over b minus a. So let's use a and b. Maybe it's easier to use this because in the book it's written in this form. So we have a and f of a, and this is b and f of b, the image of b. So if we have 2 points, we can apply this formula to give us the average rate of change. This is the average rate of change, and it's also equal to the slope for the linear function. So if we have 2 points, for example, those 2 points are 0, 0, and 3, 3. If we determine 2 points, we can find the average rate of change. The average rate of change is. Now we have f of b, let's call this a and f of a, this is b and f of b, so f of b minus f of a over b minus a, and that's f of b is 3 minus f of a is 0 over b is 3, a is 0, so the slope, the average rate of change is 1. Now for the slope, if the slope is 0, what does that mean? Slope is 0 if the function is if the function is constant. For example, f of x equals 5, because if you want to find the slope, this is x, this is y. If we graph the function, the height is 5. We can find 2 points, for example, this point and this point. So here, for example, this is 2, this is -2, this is 2, 5, and this is -2, 5. And we call them x1, y1, x2, y2. So the slope m is y2 minus y1 over x2 minus x1. y2 is 5, x1 is 5, y1 is 5, x2 is 2, minus x1 is -2. So we get 0 over 4, which is equal to 0. If the slope is 0, that means the function is constant, as we can see here. The slope is infinity, or either infinity or undefined, sometimes called, but we can call it undefined, if the line is vertical. So the line is vertical. For example, we have x equals 1. When we graph x equals 1, we have a vertical line that intersects the x-axis at the point 1. This is the graph of x equals 1. And actually, this is the graph of y equals 5. The horizontal line is given by y equals something. The vertical line is given by x equals something. So here, as you can see, the slope is undefined here, because the denominator is 0, because you can choose two values here. For example, this point is 1 and 0. This point here is x equals 1 and y equals, say, 5. If we want to find the slope, this is x1, y1, this is x2, y2. This slope is y2. y2 is 5 minus y1 is 0 over x2, 1 minus x1, 1, 5 over 0. This is undefined. So the slope can be called, in this case, we can say the slope is infinity. But if we apply the formula, we find that it's undefined. Actually, this is a very important introduction to calculus. When we deal with calculus, we deal with some similar situation when the denominator is equal to 0, but we deal with something getting closer and closer to 0 instead of dealing with 0 in the denominator. So this is undefined. When the slope is undefined, we have a vertical line.